All right. Now I would like to talk about doping. How to dope the impurities into the silicon atom or silicon lattice. Okay, you can see, for example, this is N-doping. Oh, sorry. Yeah. What does it mean for N-doping? N means N-type. But anyway, we would like to dope the so-called donor impurity. For example, phosphorus. Phosphorus, to the outmost share, actually it has 5 valence electrons, right? So if you again dope the phosphorus atom with high enough energy to kick out one silicon atom, kick it out and take the position, what will happen? I told you already. Yeah, here the phosphorus, but you take the position here, right? But for all the 4 neighbors, they're still silicon. All right. The doping, the most important idea for doping is impurities cannot have such kind of face-to-face covalent bonds. Okay. For impurities, all of them had better. If they look around, all of them stay side by side with silicon atoms, not phosphorus with phosphorus. No. In this way, the bond structure here will become too different from the others. Sometimes it will be broken. Okay, for such kind of broken bond, it's really bad for electron or Hall propagation. All right, to keep the original structure without any kind of damage, the best way is to embed one impurity atom with all the other silicon atoms. Okay, so in this way, you can see, oh, all my neighbors, they are silicon, so the structure of the overall lattice will keep the same. No much harm will be done by such kind of doping, but embed such kind of phosphorus. I have 5 valence electrons, right? But for such kind of structure, the lucky number is still 8, right? So right now we have 5 plus 4 equals 9, larger than 8. We have only 8 vacancies to be filled. So the actual one needs to be released. Say goodbye. Okay? But you must be careful. From the very beginning, silicon structure is charge neutral, right? I told you already, according to the incorrect Bohr model, the positive core inside should be equivalent to the negative electrons outside. Okay, not only for silicon but also for phosphorus. So how about phosphorus for doping? The same. It is neutral. So neutral phosphorus doped into neutral silicon. Here, charge neutral. Okay, but you can see you need to be very careful. If you release one electron out, what does it mean? The total charges here will become positive. Okay? Okay? So never mind how much you doped. Never mind how much electrons you release. The total positive charges, yeah, embedded to the lattice should be exactly the same. The total number of free electrons you release. So after doping, it is still charge neutral. Please keep this in mind. That is a very important idea. I don't care what kind of material, what kind of impurity you dope. Before doping, it is charge neutral. You dope any kind of impurity, impurity is still charge neutral. So after doping, it will be charge neutral. Okay? Yeah, that's it. In this way, okay. Why we call it N-type? Because you will release a lot of free electrons by doping such kind of material, right? So right now, you will have more electrons than holes. So the majority carriers will become n-type because electron is negative. We call it n-type semiconductor. All right? So right now, majority carrier, okay? 主要载子 Yeah. After doping, you can guess. Because from the very beginning, I told you, without doping, for intrinsic, the number of electrons, number of holes should equal to intrinsic number of blah, blah, blah. But after n-type doping, you can see, wow, the total number of electrons, free electrons, will be substantially increased. What does it mean? How about the holes? According to recombination, for holes, it is much easier to find weak free electrons, right? So, according to recombination, for example, if I increase it by 100 times, it means for free holes, it will get 100 times easier to capture free electrons. What does it mean? The total density of holes will be reduced substantially by 100 times. Exactly the same. Bingo. So I would like to tell you that after doping, this is substantially increased. That is substantially decreased. Overall, the same. The product is still the same. Okay? So you can see, from the very beginning, if this is 0, they are the same. Intrinsic impurity. But after doping, this becomes sky high. It becomes sky low, almost 0, right? Okay? That's it. So you will ask me, after doping, what is the concentration for your electron? It is almost equivalent to doping concentration. Okay, because we dope too many impurities into the lattice to generate too many free electrons. And very few of them, because as I told you, it is increased by not only 100 times. Usually, it is increased by 1 million. Okay? Wow. Wow. Okay? So, the electrons is increased sky high. Very little portion of them needs to be recombined with holes. Okay? I'm too many. Very little. Much less than 1%. No. Much less than 0.1, 0.01% of the electrons need to be recombined. So my total number is almost the same. Okay, I have simply too many. Okay, so again, the concentration of electrons will be almost the same as the doping concentration. Okay. Yeah, n-type doping. And then, because this by that equals this, so you can estimate how much the whole concentration. You just divided this by that. That's it. Very easy. Sorry, this is equal. Okay. All right, let's go for p-type semiconductor. You need to have such kind of p-doping, and again, we have boron. For usually we have boron to be acceptor impurity. Accept what? Free electron. Okay. So again, after doping, I have only 3. My neighbors, each one contribute 1. So 3 plus 4 equals 7, less than 8. So we have 1 extra vacancy. For what? To attract free electrons. Similarly, it means there is a hole. Okay, that's it. And again, neutral in charge. You are neutral, I am neutral after doping. It is still neutral. But again, we force, okay, Hall to be positive. So you still need to balance the charges. So it means what? The main body needs to be pretended to be negative. Okay, that's it. Again, in idea, the empathy is neither positive nor negative. But according to a student, for the easy understanding of the students, we pretend the whole is positive. So you also need to pretend the boron, the main body of boron, is negative to balance the charges. Okay? Okay? Whole is positive, the idea is totally incorrect. But to help you get easy understanding, I cannot say better understanding. Okay, you pretend this one is positive, then you need to pretend its mother is negative. Okay, that's it. All right. Yeah. And right now, wholes become majority carriers. Again, the density of whole right now becomes sky high. Very, very little portion of it needs to recombine with the free electrons, right? So again, right now the whole density will become almost exactly the same as the doping concentration for your acceptors, all right? And how about the electron? Electron concentration? Okay, Ni squared by Na. That's it. Okay, yeah. My concentration is much larger than yours. So I am the majority. You are only the minority. Okay, that's it. So I am majority carrier. You are minority carrier. Yeah. So majority, minority, it means for the material who dominates the current conduction. Okay? In p-type semiconductor, you have much, much more holes than electrons. So holes are majority, electrons are minority. On the contrary, in n-type semiconductor, you have much, much more electrons. So electrons are majority, holes are minority. Keep this in mind. Okay, that's it. Good enough. Yeah, the same. Okay. Anyway, this is a more accurate explanation. Yeah. Anyway, after, for example, this is after n-type doping, the Fermi level will be increased very, very close to the conduction band. And according to, because right now the energy gap is reduced from this to that, it becomes very small, right? So most of the valence electrons here will become free. Okay, that is a much better, much accurate explanation according to quantum physics. But it's harder to understand because all of you, including my, I studied state physics, but right now I forgot all of them. Yeah, actually, to be a very good analog IC designer, you don't need to study such kind of very hard topics, just like quantum physics, solid state physics. No. Okay, only if you have good enough understanding. That's it. Okay, and forget about all the equations. You only need to know the tendency. For example, I told you they are exponentially distributed. Okay, yeah, roughly speaking, good enough. And how about you dope some kind of acceptors? Oh, the level will be much lower to be very close to your valence band. So it means what? The valence electrons here will jump up to here, not to there, so they are not conductive. But when they jump here, you have a lot of holes, right? That's it. Okay, better, yeah, explanation. And then, right now, congratulations, we have P-type semiconductor, we have N-type semiconductor. All right, are they useful? Again, no. Yeah, but okay. I told you, from conductor, semiconductor, right? The difference, especially for silicon, is this one. I am much worse than conductor by 12 orders. It means what? If I doped 1 ppm, ppm means very small, right? Right? Very small. But 1 out of 1 million. Wow. Compared to this, because 1 ppm means -6 order, it is still 6 order higher than the pure silicon. Right? Right? So 1 ppm doping means what? You can enhance the conductivity by 6 order. Okay? Wow. It's really amazing. But even you increase the conductivity of silicon lattice by 6 order, compared to conductor, it's still 6 order less. It's still nothing. I mean for humankind, for daily level. So if you have P-type or N-type semiconductor for, you almost no light, almost zero light, because too much resistance still there. Okay, never mind for pure semiconductor. I mean intrinsic semiconductor, P-type semiconductor, N-type semiconductor. Usually they are still useless. To make them useful, okay, the first step, yeah, for our ancestors, no, for the engineers in the past, especially material engineers, they created N-type and then P-type, and then once upon a time, they say, hey, why not? I combine both of them. Okay, bingo. That is the first device for our semiconductor. The first semiconductor device, we call it diode. Okay? Yeah, a very good story for you. When Harry met Sally, since after they can live happily. Okay? Yeah, all right. Here. With P-type, N-type coexist, we create a brand new device. We didn't find, because it didn't exist on Earth before. Humankind created. Okay, so that is the definition for invention. Okay, invention means brand new, never existed before. Okay, anyway, this is the symbol for diode. We have anode, okay, and cathode. Okay, and then what is the property? All right, let's go. Yeah, again, what will happen when Harry met Sally? In between the P-type and N-type semiconductor, the interface, we call it junction or PN junction. Yeah, one side is P-type, the other side is N-type, PN junction. Junction is very important. Okay? Again, when they meet each other, according to diffusion, right? I have a lot of holes, you have a lot of electrons. Oh, we love each other. So the electrons would like to diffuse into P-type. So you can think, oh, the holes will also like to diffuse to n-type. From the beginning, without any barrier, we meet each other. Oh, you have holes, I have electrons. Come, let's exchange. Very good, right? So, but before, please pay attention to that. Before they meet each other, they are still neutral in charge. Okay, but right now you say, hey, you have a lot of positive what? Positive holes, negative electrons. I told you already, I warned you already, because they are neutral. So it means what? The signs are positive, holes are positive. It means what? The parents need to be negative. Exactly the same. Similarly, the kids are negative, so the parents need to be positive. Okay? I only show you the carriers. I won't show you their mothers, their fathers. All right? So again, I only show you the majority carriers, this side or that side. Keep in mind, they are exactly the same charges, negative charges below it. Okay, and they are exactly the same positive charges below it. It is covered. That is only for easy, how can I say, for easy understanding, easy explanation. Okay, let's go further because they love each other. They would like to migrate to the other side, right? Bingo. Yeah. Oh, wait a moment. Okay. You can see, Hall, according to diffusion, Hall. From the beginning, the slope, according to the junction, the interface here, right? You have a lot of holes here, almost zero, not exactly, but almost zero. So how about the slope? Oh, almost infinity. So you have infinite tendency to diffuse into the other side. Okay? Yeah, they are all boys, they are all girls, right? So you can live happily. Yeah, anyway. Okay, only kidding. So from the first moment, p-type meets n-type. You can see a lot of holes would like to diffuse into the right. On the contrary, a lot of electrons would like to diffuse into the left. Bingo. That is the first step. Right? So you can see, after the first diffusion, what is covered will be exposed to the light. Okay? You are negative, your parents are positive. But you diffuse to the other side, your parents, oh, okay, nobody covered it. So here will become positive. And there will become negative. Okay? Yeah. They are called bound charges because they are bound to the lattice. Your parents cannot move. Only the kids, free electrons, free hole can diffuse to the other side. You cannot carry your parents all the way with you. No way. Because this is the so-called solid state material. It is solid, it is hard. You cannot carry the atom all the way to the other side. No. Only the free ones can move. All the others, they are bound. They cannot move. Anyway, they can only vibrate, all right, according to temperature. Right? Just like humankind. If the boys shift to the female kingdom, right, he will say he will send some soldiers to the boundary to stop the other boys to get in. Yeah. So similarly, for such kind of carriers without any life, how can they send some gas to the boundary? I mean, p-n junction to stop the others. The mechanism is very simple because I told you already. After movement, this will become positive. That will become negative. What does it mean? For the holes, you have positive charges here. The potential becomes higher. So it will become harder for the second tier to move to the other side. Right? But again, according to the distribution I show you, See? From the very beginning, when Harry met Sally, okay? Zero threshold. So everybody can go to the other side. Congratulations. But after the first tier, go to the other side, you can see, right now, the potential is increased a little bit. But still, a lot of them can migrate to the other side, right? So for the second tier of migration, the energy barrier, not the energy gap, will becomes larger and larger. All right? But if it keeps on going, as I told you already, never mind how large you push, there are still electrons and holes diffused to the other side, right? It is unstoppable. Okay? It is unstoppable. Unless you push the barrier to be infinite. Otherwise, yeah, there are still somebody eager to get married with the other side. Okay? So, yeah, somebody capable, strong enough, they can diffuse to the other side. So we need, again, another reverse mechanism to balance it. Okay? That's it. Yeah. After diffusion, for the exposed one, the area just beside the PN junction, we call it depression region. Why? Because you lack of majority carriers here, majority carriers there. It becomes a desert, almost no carrier inside. From the very beginning, a lot of electrons, a lot of holes, right? Never mind here or beside the boundary, but after migration, after diffusion, wow, people move to the other side, okay? Just like Venezuela or something, people there move outside according to the very bad president. Yeah, so it becomes a desert. It is lack of majority carriers, so we call it depression region. Almost nobody inside, okay? All of them migrate to the other side. Yeah, anyway, after such kind of diffusion, again, I told you, there is another kind of reverse mechanism to balance, not to stop, no. You cannot stop the capable one to diffuse into the other side because the distribution of the energy look like this. Never mind how large the energy gap is, you still get somebody capable of good enough energy to diffuse to the other side. Okay? But two ideas you need to know. From the very beginning, face to face, when they meet each other, the first tier diffuse to the other side, the second tier, the third tier balance. Okay? Until balance. You can see that is the so-called depression region. And again, to N-type, this will become positive. To P side, that is will become negative. So for potential distribution, you will have this kind of curve. The barrier becomes very high, and it means very few of the charges can jump to the other side. But there is still somebody can jump to the other side. How to balance it? Okay, very easy. I told you we have two mechanisms for current flow. One called diffusion, right? And how about the other? Drift. Bingo. Drift current will balance diffusion current. But how? Okay. Inside depression region, Oh, so you can see depression region is the most important guy of the whole structure. For all the others, actually, they are only supporting characters. The main issue happened around depression region. Many of the students, young engineers, they look down to depression region because depression region means nothing there, right? But even nothing there, the mechanism happens there is really important to the whole overall structure. Really, really important. Okay? Without depression region, you cannot make anything. All right? So sometimes nothing means something. Okay? Nothing here, very good. You have such kind of barrier? Yeah. So inside depression, I am talking about inside depression region, you still have thermal generation, blah, 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 blah. Okay? So for the carriers inside the depression region, for example, any kind of generation, thermal generation, kinetic energy generation, blah, blah, blah. When the electrons are pop out to the sky to become free, right? You look around, wow, this is positive, that is negative. How do you think? By nature, the electron in this field will flow to the right because the right is positive. Got it? And how about holes? Similarly, for holes, because the left side is negative, so by nature, the generated holes will flow to the left, will drift to the left, and the free electrons will drift to the right. Okay? If you would like to ask further, please pay attention to this. I'm only talking about thermal generation in depression region, but temperature is everywhere, right? So for such kind of generation, it happens not only here, but also here, but also there. What will happen? For thermal generation, for the free electrons, for the free holes generated here over there, on average, nothing happens. Why? Because it is flat. That is flat, right? So after generation, you pop up to become negative, to become positive, because it is flat. So there is no trend for you to go right or for you to go left. So on average, no movement. No movement here, no movement there, but again, the most important area, depression, will help you to push back the hole to the left, the electrons to the right, to balance diffusion current. Bingo, that's it. So we have diffusion current to the right. Okay, because holes to the right, electron to the left, the current is still to the right. Okay, and for drift current inside depression region instead of outside, inside depression region, the holes to the left, the electrons to the right. Again, they don't cancel each other. No. They help each other because this is negative. So the current for the electron is still to the left. So the total current to the left to cancel the total current to the right. Bingo. So this is the so-called diffusion current. Okay, and that is drift current, IS. Diffusion and drift, the first character is still C, right? So you can think this is shift. Yeah, shift of drift, almost the same. Okay, so this is ID, that is IS. But for IS, oh, not ICs. Okay, don't scare me. Yeah. The other meaning for S is saturation, saturation current. Later, I will tell you why we call it IS, saturation current. All right. But anyway, two mechanisms cancel each other to stabilize the whole condition. Okay, again, never mind how large the barrier is, there is still some carriers can diffuse into the other side. But inside the depression region, yeah, we have reverse mechanism to balance this portion. That's it. Okay. Yeah, that is what you can see from microelectronics. Anyway. I mentioned all those already. I explained already. Then, from the very beginning, after they meet each other, after you get enough holes diffused to the right, electrons to the left, and balanced by the drift current, they live happily since after. That's it. Stabilize, equilibrium. Nothing will happen since after. On average, they will stay the same. The same number of carriers diffused to the other side, the same number of carriers drift back to balance, to cancel each other. You get some kind of equilibrium. How to break such kind of equilibrium? Okay, let's go further. Okay. Before we go further, you may be curious, wow, how large the barrier is, especially for our major material, silicon. How large the barrier will be? Okay, see, in 1997, 1990, okay, a guy in the street, because it called street man. Wow, even the man in the street can help us to derive that kind of barrier voltage. How about you? You sit in the classroom, right? Compared to the street man, you had better perform much well. Okay. Anyway, street man help us to derive it for silicon. This is the overall equation for silicon. After calculation, we get 0.7. All right. So this is the reason why for fully to be fully on for the semi diode, yeah, you need to apply 0.7 volt. It means almost 100% of the carriers can move to the other side. But how? Later I will explain. Okay. This is the first equation I would like to show you. Yeah, why 0.7 for diode to be fully on? Yeah, the barrier by nature is 0.7 volt at room temperature. Yeah, around 20 or 25 degrees. That is the definition for room temperature. And then let's go further. You can see how wide the depression region is. The width of the depression region, actually somebody help you to derive blah blah blah. Yes, even in microelectronics, you have such kind of equation. But again, I wouldn't like you to rederive it. No. Okay. Only if you get good understanding. What kind of good understanding you need to know? You can see here and there. What does it mean? The depression width is reversely proportional to the doping concentration. Got it? The higher doping means what? The narrower depression region for each side. On the contrary, the less doping means the wider depression region. All right? That is a very important idea. Why? Again, usually new guys hate such kind of depression region because nothing inside. And again, the larger depression region means what? The higher barrier voltage. They are proportional to each other. More depression region, the higher barrier voltage. I mean for the same material. So for conduction, for the concern of conduction, the lower barrier area, the better. It can help you to conduct more current. All right? But sometimes we don't need such kind of current conduction. For example, solar cell. For solar cell, again, you need to expose. You can expose all the semiconductors to the light. All right, but I told you already, for such kind of light generation, instead of thermal generation, blah, 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 okay? Exposed to the light, what will happen? Again, the thermal generation in P region, in N region, has no impact, because the potential distribution look like this. So for the positive hole of negative negative electron generated here or there, it is flat. So they have no intention to go left, go right, and in any direction. On average, no movement, no contribution to the current generation by light. Okay? So who can help you to generate energy? Current, I mean, here. Depression region, again, according to the slope, right? The wider, the better, because in this region, after light exposure, right, the negative electron will move to the right. The positive hole will move to the left. Bingo. After exposed to the light, you can generate total current to the left. Okay? Okay? No impact here or there. The only impact is depression region. And this is what you need to know. Don't look down to such kind of nothing. Sometimes it is not nobody, it is somebody. Especially, yeah, if you, again, for current conduct, for a regular operation, the higher barrier voltage means the harder to conduct current. Okay, for your circuit. But on the contrary, for the other application, just like solar cell, yeah, the larger barrier voltage means the better. The wider depression region means the better. Yeah. So again, if you would like to conduct, to generate more power for solar cell, those needs to be very light. Okay? You need to be very lightly doped to get a lot of depression region. That's it. In this way, if you would like to design some kind of on-chip solar cell, you had better take advantages of the lightly doped materials, lightly doped layers. For example, P minus, M minus, blah, blah, blah. Keep away from P plus and M plus, because for such kind of high doping area, the depression region simply becomes too small to help you generate any kind of power, energy. Okay? So, but what kind of P minus, M minus? Substrate and well. Okay? Never mind what process you have on chip, the substrate and the well. They are lightly doped. So you had better take advantage of such kind of substrate and well to help you generate more energy than highly doped region. Okay? That's it. And the other issue I would like to mention that there is not any kind of regulation for you. I mean for such kind of doping concentration. Nobody require you the concentration here and the concentration there should be exactly the same. Usually not. Okay? Usually not the same. So if you have one side highly doped, plus means high doping concentration, and the other side minus low doping concentration. It means what? For high concentration, high doping concentration, the width here will be almost zero, because For example, I am too high, so this one will become very small. I mean, compared to the other one. Okay, and it means what? The depression region look like almost to the other side. It is also very important for that kind of diode structure. Later, I will mention about it for Schottky diode to my memory. Okay, yeah. Again, you don't need to be fair to everybody. Okay, oh, you get 50%, so the other one get 50%. No. That is not a good idea. Sometimes somebody can dominate the whole structure. Yeah, you will get different property. Okay, and then we can go further. If you would like to change the balance, okay, what you can do? We can apply reverse bias. All right, what does it mean? For reverse bias, this is p-type, that is n-type, and we apply positive for n-type, negative for p-type. Wow! Hey, don't forget that from the beginning, without any bias for open circuit, right? What is the potential distribution? It's already like this. Okay, n-type is higher in potential than p-type, but right now, you put more positive voltage for n-type than p-type. So for the voltage you apply, it will look like that, from 0 to positive, right? So the overall effect will become this plus that. It will become, okay? It means what? The barrier around depression region will be higher. Higher means what? The depression region will become wider. Okay? But what is the consequence? Oh, all right. Let's wait and see. From the very beginning, I mean without any bias. Yeah, for the current, for diffusion current, for P and N, they are the same, right? Okay. No, not for P and N. Yeah, for they are balanced for ID and IS. Okay. From the very beginning, the diffusion current is balanced by drift current. Diffusion current, again, out of depression region. Drift current inside the depression region. Okay, in this way, they can balance each other. But right now, the balance is broken by such kind of bias. I don't care, forward or reverse bias. If you apply bias, the balance, the original balance will be broken. You need to establish a new one. Okay? So, from the beginning, the diffusion current and the drift current, ID and IF, they are the same. Okay, but right now, with reverse bias, again, the barrier becomes higher. It means the depression region becomes wider. What is the impact? For drift current, because it is proportional to the depression region. Okay, so the depression region is increased a little bit. It means what? The drift current will increase a little bit proportionally. But how about the diffusion current? Wow, you can see you push the barrier to the right. Don't forget, except for very high temperature. Even for such kind of very high temperature, okay, it will be even easier for you to see. If you are already here and you apply reverse bias to the right, you can see the exponentially decay. Right? See? That is exponential decay. So if you push the energy gap, no, that is the barrier for such kind of diffraction region to the right, the barrier energy becomes larger, means much less carriers can move to the other side. Okay? It is exponentially decayed. So it means what? You got very much decay in ID, but only a little bit increase in IS. So from the very beginning, IS here, ID there, IS increased a little bit according to the wider depression region. But for ID, it's reduced very much, almost to 0. Right? Bingo. So after reverse bias, the total current will become, because it is increased a little bit, and this is reduced almost to 0. So, see? See? The current for reverse bias is equivalent to this one. But it is increased only a little bit, because from the beginning, the diffraction region is such wide. After you apply reverse bias, it increased a little bit. So it means what? IS is quite stable because it is not increased very huge, only very little. Okay, so in magnitude, it looked about the same. So we call it saturation current for reverse bias. That's it. That is another reason why we call it IS, S for saturation. Okay, that is for reverse bias. That's it. Almost constant, as I say, because ID right now almost reduced to 0. All right, and then let's look at the equivalent capacitance, because this is really important for your IC design in the future. Parasitic capacitance always slow down your operation, right? So you had better to reduce it. So this is the overall structure for you. Here, this is a reverse voltage, okay? If we are talking about reverse bias, from the very beginning, as I told you, when p-type and n-type, meet each other, wow, it is very easy for each side to diffuse to the other. But after equilibrium, right, it becomes harder to diffuse to the other side. If you increase the reverse bias, the depression region will become even wider. It means what? Much less charges can be pushed to the other side. Got it? The more reverse bias, it means the even harder for the charges to diffuse to the other side. So you can see the curve look like this way. From the beginning, it is easier because the barrier is so low, it's easier for you to diffuse, go to the other side. Okay? But after you increase it, less and less and less, the slope will become less and less for such kind of diffusion. All right? But this is total number of charges, and that is the reverse voltage. So how can you estimate such kind of parasitic capacitance? Yeah, from the very beginning, that is your DC condition. Q equals CV for capacitor. Okay? But for your simulation, for everything you learned from microelectronics, you usually apply small signal model. What does it mean? AC operation with narrow operation range. Okay? They are AC. They are dynamic instead of DC. I mean static. All right. So for AC, for small signal, everything needs to be linearized. Okay. So if you would like to estimate here at this point how much the capacitance is, oh, very easy. You can increase the voltage a little bit. Okay. Then you get extra charges to push into the other side, right? So the equivalent capacitance becomes delta Q over delta V. But you can make the delta very small, small signal, blah, blah, blah. Okay? So for very small difference, it becomes differential conversion. This is what we estimate such kind of equivalent capacitance. Maybe it's not you, but the EDA tools apply this concept to help you extract the capacitance. So it means what? The bias you apply to your circuit will have a very strong impact on the effective capacitance, effective resistance, everything. Okay? So this kind of heavy duty is carried by your EDA tools. We, humankind, wouldn't like to do any dirty job like this. You only need to apply proper reverse bias, then the EDA tools will help you to do all the dirty jobs. Okay? Anyway, I would like to tell you the more reverse voltage means the slope will become smaller, right? The less parasitic capacitance. Where you will get the largest parasitic capacitance around 0. Here is the dangerous area. Don't touch. If you would like to get, how can I say, very high frequency operation, please don't focus here. Around 0, that is the dangerous region for you. Okay? Because it gets the most parasitic capacitance. It will slow down your operation. Then we go further. A lot of okay. Totally, you will get this. Again, I would like to mention that are those derivations important? No, not at all. Because I highlighted for you from the first moment I told you, equations are only helpful to help you get better understanding, good enough understanding about the operation of your device, of your circuit, good enough. All right? In microelectronics, for the most, I think you can only derive for 3 transistors. But for our own design, tens of transistors, hundreds or even thousands of transistors, how can you derive anything? No, nothing you can derive. All right? So you need to get better understanding. Then by thinking, you can guess what kind of operation, what kind of impact it will have. If you tune the size, the width, the length of your device, or you tune the bias current, the bias voltage, what will be the impact? By derivation, it takes a very long time. But by thinking, you just close your eyes and think, wow, within seconds, you will get to the idea. Okay, you will know, you will get how to tune the bias, the device size. Okay, that is a very, very important large thinking for our analog IC designers. All those are, actually, I cannot say they are not important, but they are simply too complicated for you to derive. Okay, so you only get the concept. Oh, whoa, see? What kind of concept you need to have? Well, very easy, as I mentioned. The larger bias, reverse bias voltage, the smaller capacitance. Bingo, that's it. Okay, this is by derivation, but I have only explanation. without any equation. I just told you, the more reverse bias means the larger, the wider depression region. And according to such kind of energy distribution, right? The more potential area means what? The less charges you can push to the other side. So the total charges will become, it will look like this way. Instead, it doesn't look like that way, right? If it looks like that way, it means what? The higher voltage, the larger potential, right? You can push more. Oh, forget about it. Unless in this region. But sorry for that. For regular operation, the potential is already here instead of there. Okay? Okay? Yeah. Okay. If you reduce the, how can I say, the temperature to 0 degrees, you can enjoy such kind of, because nobody is vibrating, right? So for all the free electrons, they can move freely without any kind of resistance. Bingo, you will get, how can I say, pure conductor, ideal conductor, okay? Yeah. Okay, so by explanation, only by explanation, you will know the more reverse voltage, the harder to push the voltage into the other side. So the curve should be look like this way, harder and harder and harder to push instead of that way. So it means what? The capacitance, the slope becomes smaller. So the capacitance will become smaller. But if you are equation lovers, you can derive all the way, and finally you get this. And then usually the students will get lost after such kind of long time derivation. After they get this, they have no idea. What does it mean? Oh, really sad. What does it mean? What does it mean? The more here, the larger here, right? So the overall magnitude will be reduced. The smaller capacitance. Wow. For derivation, it takes tens of minutes. For explanation, if you are good, if you get good understanding, within seconds instead of minutes. No, it won't take you more than 1 minute. A few tens of seconds, good enough to get the idea. So you will know, the larger reverse voltage, the smaller, okay. Otherwise, you derive it and get it, then get lost. That is really ridiculous. But it happens all the way, okay, for young students, for young engineers. So again, I just take this for a very good example. Equations are not, how can I say? Equations are not important, but to get equations would only like to help you get good understanding. But by derivation of the equations, you need to sacrifice a lot of time. Only for such kind of very easy, the simplest device called diode. Oh, you need a lot of time. You need a lot of time to derive it. No. We need to deal with much complicated device with plenty of them, hundreds, thousands. So again, I would like to persuade you, to convince you. Understanding is much, much more important for analog IC designers than derivation. Okay? Again, you are engineers. You are not mathematicians. Okay? Physicians. No, you are not any of them. So forget about it. But for such kind of reverse bias, you need to be very careful. Right. Careful or not, you need to pay attention to another mechanism called breakdown. If you apply too much reverse bias, the diode will break down. Okay? But luckily enough, because they don't have brain, they are not alive, not like humankind. Humankind, after breaking down, we will become nuts. I mean, we will become crazy guys. Okay, it is very hard for humankind to recover after breaking down. But for such kind of device without any life, no worries. Only if you limit the breakdown current, don't let the device burn down. Good enough. Okay. After you turn, you turn it back. You don't apply so much. Okay, how can I say? After breaking down, nothing will happen. No impact at all if you limit the breakdown current. Good enough. Okay, they can fully recover after breaking down, not like humankind. All right. Yeah, but what kind of breakdown we have? Two possibilities, two kind of mechanism. First of all, we call it Zener effect because it is not created. No. It is founded by Zener. So to honor him, we call it Zener effect. Especially for heavily doped diode. Why? Heavily doped means what? The depression region becomes very narrow, right? But for silicon, the barrier is still 0.7 volt. So it means what? The narrower, highly doped diode, the narrower depression region, it means the electrical field here becomes much larger. Until what? If you have enough electrical field, how can I say? To break down the covalent bonds. Congratulations. All the valence electrons will be taken out by your very strong electrical field to become free. Okay? But how many electrons you take away, you will leave the same number of holes for conduction. Wow, a lot of. Many of them are taken away to be free, so it will help you to conduct a lot of current. We call it Zener breakdown. Okay, it only happens for heavily doped diodes. The other kind of breakdown, we call it avalanche. Avalanche breakdown. Okay, what does it mean? If the reverse bias becomes too much, because the more reverse bias means what? The higher barrier, right? The higher barrier means what? For the thermal generation inside, again, inside the depression region. Your holes, especially not for holes, for free electrons. For free electrons, it will be accelerated because this is minus, that is positive. The free electrons will be accelerated to the positive one. But it is the wrong way, right? So, according to physics, Newton's blah, blah, blah law, right? F equals ma. Wow, you have good enough force, you get acceleration. You will be speed up and to increase your speed. Yeah, further and further, larger and larger. Finally, you get too much kinetic energy. But I told you already, for such kind of drift, the electrons still need to collide with the lattice. But for such kind of acceleration, after you get good enough energy, you collide with the atom. But I have too much energy, right? So I will kick out. For example, from the very beginning, one kick out one. No much impact. But if you get further energy, one free electron will kick out two. If you get more, one will kick out three. Okay, keep this in mind. Anyway, if one kick out two, I kick out two, but I lose my energy. I lose my energy. I will stay there, right? Two out, I'm in. So you will get two extra electrons, but only one extra hole. Why? Because I stay in to kill the other one. All right? Anyway, under such kind of circumstances, one electron can generate 3 charges. 2 negative, 1 positive. Okay? So in this way, you can guess 1 by 3 and then 3 by 9. Not so much because, oh, even for the holes, it is possible. So 1 by 3, 3 by 9, 9 by. What does it mean? The total number of carriers will become, wow, even faster than exponential rise. Okay? So finally, you will kick out almost all the carriers, all the electrons, all the holes to conduct the current for you. We call it avalanche breakdown, just like the snow on the top of the hill, right? It rolls down, wow, 1 by 3, 3 by 9. Wow, we call it avalanche. It is very dangerous to cover humankind. If you are hiking, like, whoa, avalanche, run for your life. Most of the people will be killed, yeah, if they cannot escape. All right? But again, for such kind of breakdown, it is not destructive. It is not harmful. Only if the maximum current is limited. But how can you limit such kind of breakdown current? The easiest way is to have a resistor connected in series. The more current means what? The more voltage will be absorbed by the resistor. It will reduce the voltage, the current flows through the diode. Okay? Wow, I'm too talkative. Wait a moment, allow me to finish it for you. Okay? Because chapter 2 is only some kind of refresh. I help you to refresh your mind about semiconductor physics first, and then the simplest device, diode. Okay? Now I hope I can finish very soon. Very soon. 5 or 10 more minutes. Again, don't put the blame on me. I'm a passionate professor. I would like to teach almost everything I know. But nothing is free. You need to pay the time. Okay, so to the end of the semester, don't say, hey, the professor, don't stick to the clocks. Yeah, I waste your time. No, no, no. If you think I waste your time, please go away. Okay, you don't need to stay here. I hope everybody stay in the class can learn more from myself. That is my passion. That is my ambition. So please don't put the blame on me. Okay, I try my very best to teach you, to help you. Okay. That is for reverse bias. How about forward bias? Yeah. For forward bias, you can see from the beginning, it looked like that, right? I mean, for p-n junction, it looked like that. But how to apply forward bias? Positive here, negative there. So, from the very beginning, you have this. But applying forward bias, it will become what? It will become, right? The barrier in depression region will be reduced by forward bias. Fantastic. Again, from the very beginning, without any kind of bias, ID and IS are the same, right? But by applying forward bias, the barrier will become smaller. Congratulations. Here to there, to there. What you can expect? The total number of the carriers can move to the other side. It is increased exponentially, right? See? Can you see the tendency? The barrier here becomes smaller. It is pushed to the right. So you can enjoy such kind of exponential increase, for reducing the barrier energy. Bingo. Okay, so the diffusion current will be increased exponentially increased. Congratulations. But how about the IS? Again, because the barrier energy is reduced, so the depression region will also be reduced proportionally. I mean, only a little bit. Very small change here, huge change there. So you can neglect this one for forward bias. The overall current is dominated by ID, but I told you already, by reducing the barrier gap, you will enjoy the exponential increase in total number of carriers. It means in total number of conduction current. The conduction current will be increased exponentially. Bingo! That is what I can help. All right? Exponentially increased. Yeah, forget about this. Later, if I have time. So, that is really, wow, complicated. Yeah, let's go. Wow. Oh, finally, you get this. Okay? And then, do you get the point? Usually not. After tens of minutes of derivation, students always get lost. For what? Okay, for what? But after my explanation, I don't need to derive anything. Anyway, I show you this. See? What I told you. For forward bias, VD is positive. Right? The total number of carriers can be pushed to the other side. It's exponentially increased. So your ID the same. ID right now, sorry for that. ID right now is the total current. It's not the diffusion current, no. The total current will be increased substantially for forward bias. And how about the reverse bias? I told you already, right? After reverse bias, you get the drift current is almost saturated because the further you increase, it doesn't get much more increase in current, reverse current. So it is almost saturated. Actually, it is not flat. It is a little bit tilted, okay? But almost flat, very close to zero. But after some voltage, it will break down. Wow, conduct a lot of current. That's it. Bingo. That is all what you need to know. Good enough. How about all those? Forget about it. But you had better memorize it. Okay? We don't need to memorize too many equations. Very few. For diode, this one. Good enough. For MOSFET, strong inversion, I mean saturation, triode, or weak inversion, 3. Good enough. Okay? And how about the others? No. For your whole life, according to device, only 4 equations. How much time you spend for your microelectronics? How much time you spend? You need to pay for my class, analog IC design. Wow, 2 semesters. Oh no, for microelectronics, 3 semesters, including these 4 semesters. But I only require you to memorize 4 equations. That is not any kind of hard job, right? And already, I guess you already memorized this. So for most, in next chapter, you get another 3. Good enough. 4 for your whole life. But maybe you ask, hey, how about here? How about here? Oh yeah, we have a lot of equations, but you don't need to memorize them. Whenever you need, you just open your textbook. You can look at that. Or you just Google online. Good enough. But for this one, too fundamental. Okay? So I still think to memorize those 4 equations will speed up your logic thinking about how to guess if you change the bias. Oh, yeah. How about the change for your current? Blah, blah, blah. It will be faster for you to speed up your guess, your logic thinking for the operation of the circuit. All right? But I need to point out that this is not real. Why? Because we would like you to have a better vision about the property. So, if you look at anything like this, I promise you, that is the usual case you have, right? But you need to be careful because to get better vision, the scale here is zoomed in. It is enlarged. Okay? And also the scale there is also enlarged. So if you don't have zoom in here, zoom in there, all right. What is the real? I mean, to the scale, 完全等比例的. Okay, right now they are not to the scale because you zoom in here and there. Okay, so if you don't zoom in, then allow me to show you. This one will become, without zoom in, it will become this, much closer to the vertical line. Without zoom in, IS is almost 0, very close to the x-axis, and then breaking down. That is real. Okay? Because how much volt here? Sometimes a few volts, but for such kind of Xenon diode, sometimes 30 volts, 50 volts. Okay? So with such kind of tens of volts in breaking down voltage, here is only 0.7. It looks really small. Okay? So in that way, you don't have such kind of good detail for you. Oh, exponential rise. And the saturation current looks stable. A little bit tilted. Only a little bit. Yeah. So that is what we can help. That is the usual case. We zoom in here, we zoom in there. Anyway, without any derivation, only through explanation, you will get the whole picture of the diode operation. Right? So that is the power of understanding. If you understand, it will be much easier to guess what kind of operation you will get. Okay? Even you face the new devices, even you face the new circuit, you don't need to derive, then get nothing. Okay? That is, again, what I can help. I'm different from the other professors. I don't focus on any kind of equations, mathematics. And this is also the reason why. How to evaluate how good you are. Just go to the lab to tune. If you have that good logic thinking, understanding, then you can tune the circuit much faster than the others. That is what you need to achieve, not only for the class, but also for your good future for IC design, analog IC design. Okay? Don't tell me, oh, I'm very good at derivation. Well, piece of cake. Nothing for me. All right? Anyway, so we don't have any kind of quiz to test how good you are to derive the equation. That is really no good for your future. Okay, for diffusion capacitance. Okay, one moment. How about the diffusion capacitance? I mean for forward bias. Okay, we can look back this. Yeah. For forward bias, I told you, because it looks like this, right? You push here, you push there. You need to push a lot of carriers to the other side. Okay? So the tendency is totally reversed to this. Totally reversed. That is for reverse bias. The more reverse bias, the harder to push the charges to the other side. On the contrary, the more forward bias, exponentially increased. Okay, so overall, it will look like this. Okay, that is what I can tell you. For reverse bias in that direction, that is negative. That is positive for forward. Okay, the more forward bias, well, the more you can push to the other side. So what does it mean? More parasitic capacitance. Okay, that's it. that is the overall picture. I think not only for microelectronics, even for all those analog IC design textbook, they don't have such kind of overall view for you. They only derive this one, oh, with a lot of equations. Oh, you can see a portion for reverse. And the other portion, oh, after a lot of equations, oh, you get this. Even you don't get the curve. But right now, after exponential, I promise you, they look like that without any derivation. Okay? So you need to be very, very careful. Careful for what? It expands all the way, okay? Reverse and forward. All right? Don't turn the diode on and off. You turn on and turn off. Yeah, the charges, especially when it is forward bias, millions, billions of charges need to push to the other side. If you want to turn it off, you need to pull them back. It takes a much longer time. Okay? So, again, according to what I told you, don't operate your diode here and there very frequently, because the operation frequency will be slowed down very, very much. Okay? But you can say, hey, we have some need for high frequency switching, right? Okay. What I can help? Here, you can replace it with metal. Especially, for example, only 3 covalent electrons for the metal atom. Who has this? For example, aluminum. Okay? For aluminum, it has only 3. So it behaves like p-type. It is not semiconductor, but it behaves like p-type. So you push a lot of charges to aluminum, piece of cake. If you want to pull it back, because it is conductor, right? Yeah, within seconds, within milliseconds, within microseconds, we can pull all your troops back your own country. Good enough. So this is what kind of structure? Maybe we call it Schottky diode. Okay, that's it. Bingo. Again, good understanding is not only helpful for IC design, but also for device fabrication, device design. Okay, that's it. Thank you all. For chapter 2. Yeah, for all the others, equations, forget about it. Okay, so next week, we will proceed to the brief introduction for MOSFET. And after that, hopefully you can design your CMOS circuit more efficiently than before. Thank you.